makes his or her way along the stream and interviews anglers as he or she comes upon them. And it's important to note that roving surveys operate under the assumption that anglers to be interviewed on a given day are intercepted with a probability proportional to the length of their completed fishing trip. So for example, an angler fishing for only a few minutes isn't as likely to be intercepted by the survey agent as an angler that's been fishing all day. And this is a really important assumption, which if violated can result in biased estimates. And because of this potential for biased estimates, there's been a controversy going for over 40 years in the fisheries literature about the best way to estimate catch rates from roving creels. Two important papers came out in 1997, one by Pollock et al. And another by Pollock et al., where they used statistical theory and simulation modeling to show that the mean of the ratios was best for estimating catch rates using incomplete trip information from roving creel surveys. And basically, the mean of the ratios just calculates the average of the individual catch rates for all anglers intercepted on a given day. Now, for completed trips, on the other hand, they found that the ratio of the means performed best. And the ratio of the means essentially just divides the mean number of fish reported caught by the mean fishing effort recorded. And since 1997, most recreational fisheries creel surveys have been conducted following recommendations from these two papers, as we heard from Scott, for example. But despite having this established roving creel survey design, some empirical studies have shown that catch and harvest rates derived from incomplete trips may not accurately approximate those of completed trips. For example, a paper by Kenneth et al. In 2009, they conducted a roving creel survey and simultaneously conducted a catch card survey where interviewed anglers were given a survey card to mail in after they completed their fishing trip. So this method yielded both incomplete and complete trip information on the same group of anglers. And using this method, Keith found persistent bias despite using those recommended estimators, which you can see in this figure here, where the dotted line represents the ideal unbiased one-to-one relationship, and the solid line represents the actual linear model relating complete trips to incomplete trips. Now, based on their findings, they recommended using ordinary least squares regression, which is just essentially linear regression, just think of it like that, as a corrective model to help reduce bias associated with the estimators. And so when we began looking into using a method like this from this paper to develop our own corrective models, we noticed a potential problem with their analysis. Which leads me finally to the theme of this talk, which is measurement error. But before I get into measurement error, I think it's important to differentiate it from sampling error, which is, I think, the type of error or uncertainty that most of us are more familiar with. Now, sampling error is essentially just the degree to which a survey statistic differs from its true value due to the fact that the survey was conducted among only one of many possible survey samples. Now, measurement error, on the other hand, is the degree to which a survey statistic differs from its true value due to imperfections in the way the statistic was collected. Okay? So now we can move on to that potential problem with the corrective model in the Keith paper. If you'll think back to regression, it was originally devised to explore the nature of a relationship between a measured dependent variable, which is usually on the y-axis, and a controlled independent variable, which is usually on the x-axis, where levels are specifically set by the researcher to a uniform range of possibilities. So again, we're assuming no error on the x-axis. So while we acknowledge that the dependent variable on the y will always be subject to sampling error unless you do a complete census, problems arise when the independent variable contains measurement error. And this problem is known as error in variables. So if we think back to the last slide where Keith was regressing two variables, both of which were measured with error, that regression may have been subject to the error in variables problem. So let's see what happens to a regression when we have error in both variables. What does it actually do? So we can illustrate this problem using simulation. So here we simulated some data where the true model had measurement error in x, which you can see is the dashed black line here. We then ran the simulation over 1,000 iterations for a linear model where we ignored that error in x. So the true model has error. These lines in pink here ignore the error. So notice that all of the iterations have lower slopes than the true model. We then repeated the procedure, but this time incorporated a range of error in x, which produced the green lines and approximated the true model much better than the naive model in pink. So as you can see, when there's potential measurement error in the independent variable, models that acknowledge and incorporate uncertainty in both variables perform much better. Okay, so we saw what happens in the simulation, but what actually caused the slope to be consistently biased low? Over 1,000 iterations, it was always lower. So we can demonstrate this problem arithmetically by relating two variables. Zeta will be our independent variable, and eta will be our dependent variable. But actually, before I go any further with this, I want to quickly apologize for my pronunciation of the Greek letters. My dad's actually a Greek mathematician, so I'll probably use some of the more proper Greek pronunciation and some more Americanized pronunciation, so I apologize for any confusion that might cause in the next couple slides here. But anyways, getting back to our linear model, we can relate the two variables using eta equals alpha plus beta zeta, where alpha is the intercept term and beta is the slope term. And again, this is just your standard linear equation. But when we have measurement error in both the variables, we actually have to add some additional terms. Since what we're really observing is x equals zeta plus delta, where delta is the measurement error term, and x is the true value of zeta. And y equals eta plus epsilon, which we can actually further define as alpha plus beta zeta plus epsilon, since we defined eta in the previous slide, where epsilon is the sampling error term, and y is the true value of eta. So after several steps, which we won't go into, the models can be combined and reformulated as y equals alpha plus beta x plus epsilon minus beta delta, which clearly illustrates the problems with the standard linear regression model, as the error term is dependent on beta, and the term in parentheses, epsilon minus beta delta, is correlated with x. So then when we go to calculate the slope, we actually have to include the variance of delta. So given us the slope equation, the covariance of xy divided by the variance of x, which would just be your normal slope equation, but then we have this additional term, that we add to the denominator, the variance of delta. And since that term is added to the denominator, obviously it's going to drive the denominator up, which will drive our overall estimate of slope down. And that's actually called attenuation bias or regression dilution. And that's actually what caused our slope to be consistently lower in the simulation. All right, so hopefully, whether through the simulation or through the math, I've convinced everyone that error in variables can be an important concern in Angler surveys. But I want to note that this problem isn't just limited to Angler surveys or fisheries science in general. It's really common in social sciences, ecology, economics, and pretty much any work that takes place outside of a highly controlled lab environment using precise measurement instruments. In fact, the famous MIT economist Jerry Hausman argues that almost all existing data sets contain errors of different nature and magnitude, making attenuation bias so frequent that the magnitude of the estimate is almost always smaller than expected. And he even goes so far as to call this the iron law of econometrics. But fortunately, given that this is such a common problem, there actually are several methods available to deal with measurement error in the independent variable, which leads me to some of the methods that we used in this study. So in our study, we compared the performance of ordinary least squared regression, which again, remember, is just linear regression, to three common Model 2 regression types. And what Model 2 regression is, it's just referring to a family of line fitting procedures that acknowledge and incorporate uncertainty in both the dependent and independent variables, and is one of the most common methods for dealing with measurement error. So in ordinary least squared regression, the best fit line is the one that minimizes the vertical spread of the values around the line. Or in other words, just minimizes the sums of squares of the residuals, or the differences between observed and expected values. But remember, we know that with measurement error, we also can have error on the x as well. So what about just taking the horizontal spread? Well, then that just leaves out the spread in the y, so it's kind of just the opposite problem. So that doesn't really work. Well, what can we do? Well, this is where Model 2 regression comes in. So one common type of Model 2 regression that we used is called major axis regression, and it minimizes the sum of squares of the perpendicular spread from the line rather than the vertical. There's also another type called ranged major axis, that we also used, and it does pretty much the same thing, but just uses a pre-standardized range of values. And then a third type is standardized major axis regression, which minimizes the sum of the products of the horizontal and vertical distances of observation from the line. So basically, Model 2 regression is better equipped to deal with this error in variables problem than ordinary least squares regression because it can handle error in both directions. All right, and I'm not going to spend too much time talking about the creel survey method since we just heard about that in Ben's talk. other than to say we tried to conduct this part of the study on all 9 of the streams Ben talked about, but we ended up having to limit our analysis to Caterossus and East Coy creeks just because they had a high enough return rate and a high enough number of card interview matches to use in this study. And then also, in addition to the standard creel survey methods, we gave each interviewed angler an individually numbered postage-paid catch card in order to obtain completed trip information. And we also offered a $100 lottery for return cards in an effort to increase response rate and to minimize the potential for angler response bias, where only successful anglers return their cards. So when we ran the numbers, we found that catch rates differed significantly between the 2 estimators. So the mean catch rate was 0.45 for completed trips using the ratio of the means estimator, and 0.89 for incomplete trips using the mean of the ratios, for an estimated catch rate difference of 0.44 fish per hour. We also estimated catch rate using both estimators on completed trips only, and we found that differences were minimized, indicating that bias might be stemming from error in the incomplete trip data collection rather than from the estimators themselves, which is what they thought in the Keith paper. All right, so this figure shows a comparison of catch rates estimated from incomplete trips using the roving creel survey design versus complete trips from the catch card survey for the 2 study streams, East Coy and Caterossus, using ordinary least squared and 3 Model 2 regression types. And while the picture here isn't as cut and dry as what we saw in the simulation, since we don't actually know the true model, our results do fit the pattern we expect if our estimates were indeed subject to measurement error. Because notice that the ordinary least squared line in blue has a lower slope than all of the Model 2 regression lines, so in green, red, and black, since they're all robust to error and variables, whereas the ordinary least squared is not. So the Model 2 lines aren't suffering from that attenuation bias. So this is the pattern we'd expect to see if that was going on. All right, so we did see the same pattern that we'd expect with measurement error, but what's more important is actually how did these different model types perform as bias correctors, because if you remember, that's the whole purpose of all this. So recall that with the corrective models, or without the corrective model, sorry, the catch rate estimated from incomplete trips differed from completed trips by 0.44 fish per hour, which is a fairly substantial difference. But when we used ordinary least squared regression, as they did in the Keith paper, bias was reduced to 0.14, which is quite good. But estimates from the using the Model 2 bias correctors performed even better, with the range major axis corrective model performing best, underestimating the incomplete trip catch rate by only 0.04. So definitely outperformed ordinary least squares, and all the corrective models performed better than without the corrector at all. All right, so hopefully I've shown that by combining a traditional roving creel survey with a catch card program, we were able to improve our estimates of catch rate using Model 2 regression. I also hope I've convinced you that it might be worth incorporating some of these methods, or at least being aware of these methods for future creel surveys or when working with other data that might be subject to measurement error. And then just to recap quickly, some of the main findings were: we found consistent bias between estimates from complete versus incomplete trip information, similar to the findings of the Keith paper. And when the 2 estimators were compared using only completed trip data, bias was greatly reduced, indicating that the source of variation was likely driven by error in the data rather than bias resulting from the estimators themselves, again, which is what they thought in the Keith paper. And the ordinary least squared slope was lower than the Model 2 slopes, which indicates potential attenuation bias in our original estimates. And finally, Model 2 methods perform better as corrective models than ordinary least squared, which is what you'd expect with measurement error in the independent variable. And with that, I just want to thank pretty much the same people and agencies that have been thanked, but especially the DC personnel on the trout team, and Fred Henson and Sean Keeler and the creel agents who were actually out talking to anglers and handing out the cards, as well as some of my field technicians who were collecting all the catch card data and putting it into the spreadsheet. So with that, I think I have time for some questions, so thank you.